if you don't mind, let's postpone question till later and till after the talk until to gather town and start our grand finale of today's, which is the talk by Shai Ben David about, as you could see, if PvsNP can be independent of the axioms of reasoning. And so just a couple of words to introduce Shai Ben David. His work spans a really vast range from from set theory of set, really deep set theory to really practical machine learning with algorithm and complexity and logic and all sorts of things in between. And Shai can connect all those disparate things and show the relations where, it's hard to imagine that there could even be relations. For example, independent result of a machine learning problem. This is one of your NeurIP's best paper awards, right?
No, not this
one. That one? Not this one? Okay, so you have other papers which got NeurIP's best paper awards and such. Anyway, so Shai's work spans huge area and it's really beautiful. And today he's going to tell us about that really cool result about Sat and PvsNP and independence. Please.
Okay, yeah, so I'll try to be not technical. I know we're running behind time. So yeah, so I want to look at this question of whether P versus NP can be independent of set theory. And here, I mean, as in contrast to what Sasha was saying, when you look at negative results, the stronger the system you can show that cannot prove something, the stronger the result is. So I'm really interested in much stronger systems. So I'm not going to talk about Sat or anything, how to solve Sat, but so what was the talk about? So when you're faced with some hard mathematical problem, there's always the temptation to think that maybe this problem is inherently irresolvable. Maybe the reason that we fail to find answers is not our lack of wisdom, but rather that no answer, no proof exists. I mean, that's following Gödel, we know that this is always a possibility when we're facing an open problem. So the goal of this research was to see, try to ask, why do we fail to resolve some basic computational complexity questions? Could it be that P versus NP or other computational open problems are unresolvable in set theory, which means we have no tools of proving that's the answer. And more concretely, is it likely that, that the tools that we have in mathematics are inherently too weak to determine relationship between complexity classes? So, I mean, if we believe in such a direction, then we should direct our efforts to answering these logic-oriented questions rather than struggle with directly computational complexity issues, because maybe it's hopeless. Maybe by showing that, I mean, that's the kind of the line of research that Sasha was taking and others in this community that don't try this direction because it's futile. So what do we know about independence proof? Just to remind everybody of independence proof of set theory. So Hilbert's program was the hope to develop a formal method that will resolve all mathematical questions. And of course, Gödel's incompleteness result showed that this plan is bound to fail. Every reasonable mathematical framework has irresolvable question, and we will call a problem independent of a theory T if T cannot prove neither the statement S nor its negation. And Gödel showed that the consistency of a theory T is always such an independent statement with respect to T. But of course, what we are interested in is, are there relevant real mathematical questions that fall in this category of being unresolvable by set theory, which means unresolvable by what we call mathematical proof. Okay, so what do we know about that? So what is the set theory that we look at? So a formal theory that defines, kind of commonly define what mathematical proof is about is the set theory, ZFC. There is a slightly weaker theory which talks about arithmetic, pan-arithmetic, we all know it. And just to mention that pan-arithmetic is equivalent to set theory if we just delete the statement there exists an infinite set. So, and since ZFC can prove the consistency of pan-arithmetic, we can build in ZFC a model for number theory. Then we know that it's strictly stronger than PA, even with respect to statements about natural numbers, because the statement pan-arithmetic is consistent can be phrased as a statement about natural numbers. So here is a statement about natural numbers that you can prove with ZFC, with the assumption, with the extra axiom there exists an infinite set. And you cannot prove this statement in pan-arithmetic, although it is a finitary statement about natural numbers. Okay, so that's kind of the background. And Paul Cohen showed that there are really questions that are independent of set theory. The continuum hypothesis and is a kind of a sounding example of this. And since then, there have been many, many independence results in set theory. It started with cardinal arithmetic and infinite combinatorics, group theory, topology, functional analysis, algebra. And recently we had, as Antonina mentioned, we had an independence results of set theory for a very, very basic question in machine learning. So what can we say about independence results for computational complexity? Do all of this kind of machinery of being able to show that things are independent of a strong theory, does it apply to computational complexity statements? So there is an old result of Hoploff and Hartmanis that says that for any theory T, we can find a Turing machine such as the oracle complexity with respect to this Turing machine cannot be decided in T. This is kind of a diagonalization trick and talks about the oracle P versus NP with respect to some specially crafted oracle. So that was kind of the first result. And then there were several results of independence of weaker fragments of arithmetic. We already mentioned here some. First there were artificial fragments that were kind of meant to be weak enough so that you will not be able to prove much with those weak fragments. Then there was bounded arithmetic independence, like the famous independence results of Sasha, and all kind of limiting the proof techniques. So relativized the proofs, that was the oracle result of Baker, Gill, and Solovey, and then Rasbov and Rudich showed that if you limit the proofs in another way, it's exactly what Sasha was talking about, then there are statements you will not be able to prove, and then later there's the algebraic proofs of Aronson and Wingersohn. But can we prove the independence of P versus NP from set theory? Could this be the case? So there are inherent limitations. The point is that to realize that since Paul Cohen in 1960, Paul Cohen introduced the technique of forcing, and in some sense, we do not have any new techniques for showing independence of set theory. In a high level, they all follow the same pattern. I will not get into describing this pattern, but important to notice about it, that all the proof techniques that we have for showing independence from set theory, they cannot show independence of any statements that involves only natural numbers, only finite sets. So we do not have any technique that has a hope of showing independence of statement like P versus NP, because those are finitary statements. There exists a Turing machine such that, and there exists a case such that for all formulas and so on, everything is finitary. All the tools that we have for showing independence from full set theory can be shown not to be able to show such independence. So we have to go to, so that's what I'm trying to explain why it's a finitary statement. It's for every code P, there is a Turing machine and a K, and so on. We know that P versus NP can be written as a finitary statement in the language of number theory. So what can we hope to prove? So I'm saying we don't have any tools that will be able to show independence of P versus NP of full set theory, but what about non-provability from Peano arithmetic? That's kind of the next best thing that we could hope for. So this is a weaker theory, and a weaker theory, it would be easier to show statements that it fails to prove, naturally. And it will be a very interesting result because independence with respect to Peano arithmetic would be quite satisfactory. It will tell you that without using a statement, there exist infinite sets, we will not be able to resolve our complexity questions. So showing independence of Peano arithmetic, I think, will be a kind of, could be something to hope for as a mathematician, because it really tells you that we cannot resolve P versus NP. I mean, the possibility that for having to resolve it, we have to assume the existence of infinite sets or even stronger infinite cardinals does not, we have no way of incorporating or even imagining how it could be relevant. So this could be an interesting goal. So I can go back to my first slide. What I'm saying is, rather than trying to solve P versus NP, maybe what we should do is try to show that it is independent of Peano arithmetic. If it's independent in Peano arithmetic, in some sense, our efforts to show it, to prove it, are bound to fail. Okay, so do we know of any independence from Peano arithmetic of real mathematical statements? So as I mentioned before, we do have results about independence from ZFC, and of course, there are independence from Peano arithmetic, but these are all about statements which involve infinite sets. So do we have any statements about independence from Peano arithmetic of real mathematical statements? Of course, the consistency of Peano arithmetic is independent of Peano arithmetic, but we want to talk about inherently mathematical statements. So the first such result was Paris and Harrington, and that was a very big breakthrough at the time. They took a natural version of Ramsey theorem that we can prove in ZFC that this is a true theorem. It's just the usual Ramsey theorem, but just, I mean, I will not repeat it, but just mention to those that are familiar with Ramsey that the only addition here is that the homogeneous set, that the existence of this set is guaranteed by Ramsey theorem, should be larger than the first natural number in this set, which seems like a small minor addition to Ramsey's theorem, and it's really indeed provable that it's true, but they showed you cannot prove it in Peano arithmetic. So that was kind of giving hope that there are mathematical statements about finite sets that are independent of Peano arithmetic, although they're provable in ZFC. The question we are aiming for is to ask, is it likely to be the case for P versus NP or other computational complexity problems? So there are similar results later, statements about natural numbers. It's fun to read these things, the Hercules and the Hydra. I don't know if you heard about this. It's kind of a puzzle that you have a tree and you have leaves from the tree, which are heads of the Hydra, and you are Hercules and you have a sword and you are cutting heads, but each time you're cutting heads, it grows more heads, and it grows more heads in a scary way, the formula. And still one can prove that no matter how bad as Hercules you are, you will eventually kill the Hydra, but this eventually is very long. And to prove such a system, to prove such a statement, we can do it in ZFC, but we cannot do it in Peano arithmetic. And again, it's a finitary statement. You're playing a game against a finite tree, which is the Hydra. the interesting relevance to us is that the structure of P not equal in P is syntactically, it looks the same as the Paris-Harrington, because the Paris-Harrington is a Ramsey theorem. It says for every arity and size and the number of colors, there exists a homogeneous set of such size. And here, the P not equal in P have a very natural, a very similar syntactic structure. It says for every x, there exists a y such that phi xy, which is like the Ramsey. For every parameters, you have and size, you have a homogeneous set. And the statement, this set is homogeneous and of this side, does not contain any unbounded quantifiers. And it's the same with P versus NP. Just you want to show that for every program and every bound or the polynomial of the runtime of the program, there exists an instance of Sat such that this program will give you the wrong answer. So the statement is syntactically looks like the Paris-Harrington. So we could hope that maybe we could show a similar result independent of pair arithmetic for P not equal NP. Okay, so that's what I was set to try to understand. And the conclusion of this work, if we jump right to the end, is that if on one hand, if Sat can be solved in almost polynomial time, so say P is not equal in P, but Sat can be solved in time which is very, very close to being polynomial, and I'll elaborate on it later. If Sat can be solved in almost polynomial time, then you cannot prove that P is not equal in P. And now the concrete notion of almost polynomial depends on the theory in which you want to prove it. So for every theory, there is a notion of close to polynomial, such that if NP, if Sat can be solved in such close to polynomial time, then that theory will not be able to prove the separation between P and NP, because the Sat has a solution that looks almost like polynomial, and the theory, the almost will be so fine that the theory will not be able to distinguish between the two. So that's not so much of a surprising result, but it's something that's worthwhile to bear in mind, and I'll get back to it a bit later. But the surprise here is that we also can show the other direction. So if the theory is sufficiently strong, then the reverse statement also holds. Namely, the only possible reason for failure of the theory to prove that P is not equal to P is that Sat can be solved by an algorithm which is almost polynomial time. So in some sense, it says, loosely stated, that if you can prove that a strong mathematical theory cannot show that P is not equal to P, you will imply that Sat has a solution which is almost polynomial time. So solving the logical statement, the higher level logical statement, P versus NP is independent of set theory, will be as hard as coming up with a polynomial, almost polynomial time for Sat. So in some sense, that's the main conclusion of this talk, that there's no point of, you don't get much advantage by struggling with logic and trying to show that P versus NP is independent of set theory, because this will be as hard as showing that you have a polynomial algorithm, or almost polynomial algorithm for Sat. Okay, so that's, at this point, I said the most important things of the talk, and now I want to go a little bit into the technical details and kind of convey the intuition, which is not so complex at all, of why this is indeed the case. So we would consider, what do we mean by almost polynomial? I'm talking now about Sat has a solution which is almost polynomial time. So what do we mean by almost polynomial? So we look at running time, which is n to the fn, where the exponent fn grows very, very slowly. So it means that the running time has a constant exponent for huge stretches of input length. So the function fn, I want it to grow very, very slowly, the exponent of n of the runtime. And if the function grows very, very slowly, we can view it as the inverse of a fast-growing function. So it will be, in some sense, it's easier to talk about how fast a function grows rather than talking about how slow it does. So we'll talk about the inverse of the function, which is the exponent of the runtime. So here are some fast-growing functions, the Wiener hierarchy. So this is a way of constructing very fast-growing functions. So f1 of n is 2n. And now for every countable ordinal lambda, f lambda plus 1 of n is just you apply f of f, you compose n time f lambda and apply it to n. And if you take a limit ordinal, then you also have to define it for a limit ordinal. And for a limit ordinal, you just, at the n step, you take a sequence, delta n, that converges to delta, to your limit ordinal, and that to compute f of n, you apply the function composed delta of n times. So this is a way of defining a very fast growing functions. The Ackermann function is just f omega is the first infinite ordinal in this sequence. Is already the Ackermann function. But then, as we see here, we can keep going. We can applying it further and further and further and get faster and faster growing functions. That's the kind of the functions that we will talk about, whose inverses will be the exponents of the runtime, if indeed you could prove independence of P versus NP. So just to demonstrate here, I mean, this is a sophisticated audience. I don't have to convince you, but like f2 of 3 is already a crazy number. Somehow something hides it for me, but yeah. Anyway, anybody can do these calculations. It's crazy fast growing. Even f3, f omega is Ackermann's function, and we go beyond that. Okay. Now, how far beyond that we go when we want our functions to grow very, very, very fast? So it's common to denote by epsilon 0 the first ordinal such that omega to the power alpha equals alpha. The powers here are ordinal powers, and I will not get into the definition, but this is the limit of omega, omega to the power omega, omega to the power omega to the omega, and we take the countable limit of this. So this is epsilon 0, and we will be interested in the function f epsilon 0. So we take this Wiener hierarchy and we push it and push it and push it. We go through Ackermann function is just here at f omega, and then we keep going and going and going and going, and we get to this stationary point, fixed point of this function, and we take this crazily growing function. Why do we care about this function? So we care about such a function because it has, I mean, the next step is the way I connect fast-growing functions and complexity conjectures. I mean, this is fun to talk about fast-growing functions and Hydra and so on, but it does relate to computational complexity. So how do we make the connection? So given a complexity class which you can enumerate as a countable set of algorithms, as some canonical enumeration of the class. I guess this is what Pavel was calling a syntactic class. And given a language, I can define a function. And the function, it measures how well can this class approximate the language L. So this function at the point I, it is the maximum over, so I go over M1, M2, M3, and so on up to Mi, and I see which of them can compute L correctly on longer initial segments. So again, I go over all functions. Here is my class, M1 and 2 and so on. I'm going over at point I, I'm going over all the first I machines, or first I programs. And then for each of them, I look at the minimum point where it fails to compute my language L. And I take the maximum. So this tells me how many machines do I have to consider in order to correctly compute the language L on the first so how far can any of the first machines can compute my language? This is what we are doing here. So we define a function that measures how well can a class of functions approximate a given language. And it is easy to realize that this function is total if and only if L is not in the class. Because if L is in the class, there will be some I such that there will never be a failure. This machine, MI, will compute the class correctly. And we are just looking at the first time that all the first I machines fail. So this is a total function. For every I, there is a number R of I, if and only if the function is not in the class. And furthermore, the faster this function grows, the closer is L to the class. Because it means that fewer machines, right? F of I tells me how far could any of the first I machines compute L correctly. So if it grows fast, it means that I need few machines to compute big stretches, L on big stretches of X's. So the faster this function grows, the closer is the class, the function, the language L to the class C. So here we kind of measure how far, it's not just P not equal NP, but I'm trying to measure how far is Sat from the class of polynomial time functions. So it gives a quantitative measure. And this is the function that will apply our knowledge about our discussion of fast-growing functions. So we enumerate all p-time machines, and we assume that we have some kind of easy mapping, computable mapping from index I to the code of the ith machine, and we can, without loss of generality, assume that the ith machine is bounded by n to the log I. I mean, they're all, we're just enumerating polynomial time machines. And then we can get this nice connection between this function R and the computational complexity of computing Sat. So if R is this approximation function of Sat by P, then Sat is in deterministic time d to the log g of n for every function g that bounds R minus 1. So now let's stop and see what it means. R is how easy I can, how far I can approximate Sat. R is a function that if Sat, that grows very fast. So R minus 1 is a very slow growing function. And so G is just a computable function that upper bounds R minus 1. And it means that if Sat can be approximated well by this procedure, by enumerating all polynomial time machines, then Sat is in deterministic time, which this is a very close to constant, very slow growing function, because R is fast growing, R minus 1 is very slow growing. I take the log of it, and so I have this in the exponent. The exponent is almost a constant. So we're using fast growing functions, we're looking at the inverses as a way of measuring how close Sat is to P. And the corollary is that the approximation rate of P by Sat gives us a notion of almost polynomial time algorithm for Sat. So if the approximation rate is a fast growing function, then Sat is really almost polynomial. The exponent is almost a constant. Okay, so at this point, we have the ingredients for our reasoning. We have the notion of fast-growing function and the relation to Sat and the class P. But of course, what we want to do is relate it to probability. So what's the connection between this and probability, or in particular to the probability of P versus NP? So a function is called probably recursive. I guess you all know it. If you can prove in your theory that it holds, that I have an algorithm that computes this function and holds on every input, and probably recursive functions with respect to PA and PA1. I haven't yet defined PA1, I'll define it in a second. It's the pi1 closure of PA. It's the same, so we can talk about being provably recursive without making this distinction. And there is the Wiener theorem. And the Wiener is from this hierarchy. And the function is every f alpha for alpha less than epsilon 0 is provably recursive. And this is if, in some sense, it's if and only if. If a function is provably recursive, then it is dominated by some f alpha. So this Wiener hierarchy, what it gives us is a way to determine how fast can a function grow and still be provably recursive. Still, we could prove that for every x, there is f of x. And the answer is that roughly the bound is this f epsilon 0 in the Wiener hierarchy. So the corollary is that if a function grows very fast, it's not dominated by any of those functions, then Peano arithmetic and its closure by pi1 functions, by pi1 statements, cannot prove that the function is total. I guess I don't have time to explain the result. It's a classical result. It's a beautiful result, but if a function grows too fast, you cannot prove that this function is total. And the Paris-Hamilton, actually, the proof that Peano arithmetic cannot resolve this Ramsey type theorem is exactly by showing that the Ramsey number, that you take parameters and you want to ask how fast should your graph be in order to get such a homogeneous set, is such a fast-growing function that it's beyond the scope of what Peano arithmetic can prove it is complete. And in Peano arithmetic cannot prove that it's complete. It cannot prove that for every input parameters, there is indeed a large enough graph that will give you a homogeneous set for these parameters. So this is exactly the tool, the machinery behind the Paris-Hamilton independence result. And most of the proofs of independent from Peano arithmetics of statements that we can prove in ZFC, in set theory, have this kind of nature. They generate a very fast-growing function and show that this fast-growing function is beyond the limit that is stated by Wiener's theorem. So this repeats in other independence proof with respect to Peano arithmetic. So what we can conclude here, that if the approximation rate of Sat by P is very fast-growing function, then Peano arithmetic cannot prove that P is not equal in P. And so if Sat can be solved by an almost polynomial time algorithm, then Peano arithmetic will not be able to prove that they are different. Okay, so that's one direction of our theorem. Maybe the more interesting direction is the other direction. So the inverses of fast-growing functions are functions that are very, very almost constant. They're on big stretches. They're constant. I'm trying to rush because I see the clock that we're getting too close to 2 o'clock here and to the end of the recording. So what I'm saying is that if a function goes very fast, if this function R, the approximation, goes very fast, then there are long stretches on which Sat can be solved in a fixed polynomial. So the next step is showing that this is the only reason for non-probability of P versus NP. And I show it with respect to the theory PA1. PA1 is I add to Peano arithmetic all the pi1 true statements. Now PA1, so it's Peano arithmetic plus all the pi1 formulas that are true in standard models of arithmetic. And what do we know about this property of PA1? It's not a recursive theory. That's a big negative, but there is some notion of some sense of representation independence. I mean, it's exactly the theory that we need in order to be able to show that if you have two Turing machines, to prove that two Turing machines that compute the same function are indeed computing the same function. So in order to show representation independence of Turing machines, we need the theory PA1. And so it's, in some sense, it's a natural theory to consider when we want to talk about independence of runtime on Turing machines. And we can also, nice properties, if P equals NP, then PA1 can prove it, because you can have this polynomial time algorithm, and PA1 can prove the statement for every input it computes Sat correctly. Okay, so we switch to the theory PA1, which is much stronger, and now we have the theorem that PA1 proves P equals not equal to P if and only if the approximation rate of P is low. Oh, in other words, so I mean, before I talk about the proof idea, what we care about here is to show that PA1 will be able to, if Sat is far from P, PA1 will be able to show it. And the only reason that it cannot show it could be that Sat is very, very close to P. And the proof idea, I guess we don't have much time for proofs now, but we can write this as a pi1 statement. So the conclusion is that if PA1 fails to prove P not equal to P, then Sat has almost polynomial time algorithms. And more on the significance, so I want to show that if PA1 cannot prove that they are different, I mean, then in some sense we cannot distinguish independence proof between PA1 and PA, because the generic way in which we show that the theory does not prove some statement, the Paul-Cohen forcing style, is to start with a model. We assume that the theory is consistent, so we have a model M. We construct a submodel in which you get the opposite of the statement, and such a submodel will also satisfy the pi1 theory of the first model. So what I'm saying, any tool that we have with the hope of showing that something is independent of Peano arithmetic will also show us independence of PA1, and therefore, if we could show independence of Sat, of P versus NP, it will mean that Sat is very close to P. So this is the bottom line. So if it is provable that P versus NP is independent of PA, then Sat can be solved in deterministic time t to the g or n, where g is a very, very slow growing function, or g minus 1 is a very fast growing function, which will mean that Sat is almost in P, and that's if and only if statement. I think I've just, we have similar results for silicon complexity. We can show that, for example, if Peano arithmetic cannot show if P versus NP is independent of Peano arithmetic, then there are no one-way functions. And all kind of results in this nature, but I'm out of time, so I will stop here and take some questions, if we can still take questions.
Thank you so much. Yeah, please ask questions, and sorry for running over time, but please do ask questions. If nobody asks, may I ask a really naive question?
I have a question.
Oh, yeah. You have a question? Okay,
Yes,
go
yes.
ahead.
Okay. Does the proof technique also allow you to go further down in the strength of the theory? For instance, to replace piano arithmetic by I sigma 1 and f epsilon naught by Ackermann?
That's an interesting direction. It seems that, I mean, it's an interesting direction. I haven't thought about it. I haven't thought about weaker theories. I mean, as Sasha was saying right at the start, I come from working on ZFC, but yeah, I think it's a very interesting question. It's not inconceivable.
Okay.
More questions? Well, oh yeah, please, Pavel. Yeah.
Yeah, the comment. So I understand the message is that the problem is that we are not able to distinguish between PA and PA1. We are not really able to understand what are the basic things in piano arithmetic. We know what is the induction, but if piano arithmetic was formalized with some stronger basic theory, then everything that we are able to prove about piano arithmetic would be the same. And this is what I completely agree with you. But I would like to add that the similar thing is in complexity theory, that we are not able to distinguish computations that have different basic operations, like say if we allow Turing machine an access to Oracle and say, well, what the Oracle computes is the elementary operation. So then various things can happen, and this is the relativizations. So that
I think it's an interesting analogy.
Sorry?
I think it's a very interesting analogy, right?
Yes. Okay. Thanks.
Actually, a question to both of you, because I kept thinking about the relation between your talk, Shai, and Pavel's talk. Pavel talked about semantic classes and the question of complete problems, and you heavily use the fact that P is a syntactic class.
Right.
Is that right? So is there any kind of connection between those?
Yeah, I really don't know. I mean, I use very heavily. I mean, all of this line of all of this machinery is about syntactic classes, right?
And Thomas is asking you to show the second last slide again.
Okay. This one or the before that?
You can unmute and share.
Before that. Yes, thanks.
Right, yeah. This is about why we cannot distinguish PA1 from PA that Pavel was talking about, yeah. So do you want me to repeat it, or you want to ask something about it?
No, thank you.
Oh, okay. Yeah.
So, Shai, I have very naive question. So assume that I am telling you that NP is not a subset of quasi-polynomial time in the real world, right? It means, or maybe I missed something, you are saying that it implies that P is not equal to NP slightly weaker statement is provable in piano arithmetic.
Right.
Is it what you are saying?
Yeah. Yeah,
Okay.
this is a rough way of putting it, right.
Sounds very strong to me.
Yeah.
No, it's not provable in piano arithmetic, it's provable in PA1.
And that
No,
it's
PA, I'm sorry. Move it one slide further, or where you have a result here. It says PA.
Yeah, but here it is here I have the caveat by any method known today. So what Pavel was saying correctly, I mean, provably we can show it will be provable in PA1, but there is no mathematical tool that will distinguish PA1 from PA. So now we have to take a second step on top of it and saying by
okay.
existing tools.
Okay, good. Okay, thank you.
More question, comments to any speakers? To and from any speakers? Okay, thank you very much, everybody. This was such a fantastic session. Sorry for running over time, but I don't want it to end. This is fantastic.